address is 3, so it goes to this location, and the branch history table, the outcome is 0, 0, indicating that the predicted outcome should be not taken. So, but this instruction states, since the x17 has a value of 18 because of the execution of the first instruction, so these two registers have same value and branch equal is true actually, and it goes to PC plus 28, which is 12 plus 28, it goes to 40. So this should be the address of the next instruction. But since the branch history table has predicted as not taken, it goes to the address 16. So in the instruction, I mean in the execution phase, the actual outcome is given as taken, which is against the predicted outcome. So the value in this table, in this branch history table, is erased from 0, 0 to 0, 1. As you can see in this saturation counter, we are in this state 0, 0, and we have predicted it as not taken. So 0, 0 indicates not taken, but the actual outcome is taken. So it moves from 0, 0 to 0, 1. So that's why. So in this branch history table, it goes from 0, 0 to 0, 1. Next, so in the 44th location, again this instruction has come. So the address is same. So generally we have a branch history table whose location, I mean whose size is equal to the number of branches we have in our instruction, so that there is no, so there is no two branches which access the same location. So as usually the last 3 bits are used for indexing. It goes again to the third location. Now in the third location it is 0, 1 instead of 1, 0, it is 0, 1. So 0, 1 also indicates it is not taken. So from 44, it goes from 44th location, the PC address goes to 44 to 48. So the instruction fetch, instruction decode, and execute states happens. After the execute state, the actual outcome comes. Since this branch instruction is true, the actual outcome turns out to be taken. So again, the branch history table is changed from 0, 1 to 1, 0. So which is taken. So as you can see in this table, we are in the state 0, 1. The outcome is taken. The predicted outcome is not taken, but the actual outcome is taken. So it moves from not taken to weakly taken state. So 1, 0. So the branch is the entry in the branch history table changes from 0, 1 to 1, 0. And then let us suppose in the 108th location, whose address is this. So again, it goes the last 3 bits. It goes again to this third position. So here now it is 1, 0, which is weakly taken. So now the branch is taken. And then in the execute state, the outcome of this branch, equation comes, and that outcome is also taken. So now it moves from 1, 0 to 1, 1. So which is strongly taken. So like this, the branch history table is always, I mean, it goes on updating according to the finite state machine which has been designed. So for this, for not taken to taken, to strongly taken, there are, from not taken to taken, the outcome has to, the predicted outcome has to be gone wrong twice. So this is the 2-bit prediction scheme. So this is called the local predictor because this is because the branch equations are mutually exclusive. There is no dependency on the previous branches. So these are executed standalone. So hence they are called as local branch predictions. So if we see this Verilog code implementation of this local branch prediction, so this branch predictor has a series of inputs which has actual outcome to verify whether the predicted outcome and the actual outcome are matched or not. If they are matched, there is no problem. If there is a mismatch, there has to be a state change. So that's why this is the input. This is the instruction to know whether it is a branch instruction or not. So the PC address is used to know the address of the bits in the PC address is used to access the location of the branch history table, and then branch signal enables us to know whether the branch signal has come or not. And then this flag bit is used to know the discrepancy between the actual outcome and the predicted outcome. So basically it's an output of the XOR gate. whose inputs are predicted outcome and the actual outcome. So when there is a discrepancy, this flags 1, indicating that there is a mismatch and there has to be a change in the state in the branch history table. So coming to the coding part, so I've taken a branch history table whose there are 8 number of locations, and each location has 2 bits since it's a 2-bit prediction scheme. So there's a 3-bit address to access which acts as an index to access this branch history table location, and then the predicted address. So initially I have assumed that I have filled the branch history table with all zeros, indicating that none of the branch is taken. I mean, the prediction is always not taken now. So whenever the instruction is come, if that instruction turns out to be a branch instruction, it turns out a branch instruction, it takes the address is taken from the PC value. It goes to corresponding branch history table. From the bits which are stored in that location, the predicted outcome is maybe true or false. So based on that, the predicted address is driven, which may be PC plus 4 or PC plus 6, depending upon whether the predicted outcome is taken or not taken. So after the actual outcome, after the flag bit has come, it states that whether there is a discrepancy or not. If there is a discrepancy, the state has to be changed. So this is the implementation of the FSM which have you seen before. So this is the simulation results. So as you can see, so in the 12th location I have shown before, so there is a branch which is initially predicted as not taken, so hence it goes to 16th location, and in the execute state here, you get the result. The flag is 1, which shows it's a discrepancy, so all the instruction fetch are flushed, and then the original branch address, which is 12 plus 28, which is 40, the instruction at the 40 location is fetched here. So again, similarly in 44 there's another branch instruction which is also predicted as not taken, because in this third location, which corresponds 12, as I've shown before, the 12011 is there. So the third location is accessed. Since it is the state is 01, the prediction is not taken. And again, in the execute state, the actual outcome has come. So it states that there's a discrepancy. So the state has been changed from 1 to 2. So now the state indicates that it has to be taken, and whenever the instruction comes again, the branch instruction comes again, so I have written that branch instruction and in the location 108. So this location also, the address of the 108 also corresponds to the same location, which is 3. So now in this 3, the state is 2, 10. So indicates that it has to be taken. So hence you can see there is no discrepancy in the flag. It is always, now it is 0. So likewise, this branch prediction is implemented. So that is the local branch prediction. So as I've said, in the local branch prediction, there is no, there is no influence on the other branches. So generally, if you can see, if there is an instruction, if a equal to 2, that is assigned a equal to 0. If b equal to 2, that is assigned b equal to 0. And if a is not equal to b, then let's say there's some code going on. So let us suppose if this is true, translating this high level language corresponds to branch instruction in assembly language. So if these two branches are true, then it is always sure that this branch is not true, because A and B are assigned to same value. It means that A and B are equal. So this will always be false. So this branch instruction is influenced by the previous